Amino acid tryptophan, as well as the other aromatic amino acids, so these ones with these resonance stabilized rings we'll talk about, they absorb UV-280 light, so light with a wavelength of 280 nanometers. If you shine this UV-280 light at them and then look to see how much of that light is stolen, you can then see is protein present, and if so, how much protein is present. If you know the composition of a protein, so how much of each of these aromatic amino acids it has, you're then able to get a value called an extinction coefficient that you can use to determine the kind of precise concentration. Or if you have a generic mixture, you can use a value that's given for a sort of average protein. This is only one way to measure protein concentration. So another method is like a Bradford assay. These different protein assays, ways to quantify how much protein you have, they all kind of have their pros and cons. But today we're going to focus on this UV-based method. And so let's step back and think about what actually are we talking about? What do we actually mean by light? When you think about light, you might think about that stuff that comes out of your light bulb. But that's actually just one tiny little portion of the electromagnetic spectrum. Visible light is actually going to be the same type of thing as infrared, microwave, radio. And if you go in increasing energy, ultraviolet, X-ray, gamma rays, all of these are just different versions of light. And light itself is just little packets of energy called photons that travel in waves. All energy travels at the same sort of linear speed, the speed of light, but different wavelengths of light have different amounts of energy in those little photons. So if those photons have a lot of energy, they're going to be going back and forth, or up and down and up and down and up and down a lot more, so that they still travel at the same linear speed. And if you started at one side of the room, they'd reach the light would reach the other side of the room at the same time, even though the one would be kind of traveling a lot more because it will be kind of going back and forth a lot. So the higher the energy, the shorter the wavelength and the higher the frequency of those little waves. You can think of a grandpa and his grandson walking alongside one another, and the grandson's going right and left and right and left and right and left, so that he travels at the same speed as his grandpa, but he's got a lot more energy. So we have a shorter wavelength, higher frequency, higher energy. Conversely, if you have lower energy, you'll have a longer wavelength and a lower frequency. So now think about light as little packets of energy. Different molecules are going to be able to absorb light of different wavelengths because they need different amounts of energy in order to excite electrons in them. I'm not going to go into the details here, but if you think about a molecule, it's made up of atoms, and those atoms are made up of subatomic particles, including electrons. Those electrons can live in different sort of energy levels, and if they get the perfect amount of energy, they can travel from one energy level to another, similarly to going from different floors of an apartment building. Just like different apartment buildings, kind of like the ceiling heights might be different in different apartment buildings and different floors and stuff, molecules will have different electron levels, and different amounts of energy will thus be needed in order to go between them. This makes it so different molecules are going to absorb different wavelengths of light. To complicate things even further, some molecules will be able to absorb multiple wavelengths of light because they will have multiple parts of them that have electrons that can get excited. So if you were to go and you were to shine light of every different wavelength, you would see probably that there would be multiple kind of absorbance maxima, so places in which the molecule wavelengths that the molecules are going to absorb a lot of. And then there's going to be some sort of wiggle room on either side, so you get kind of this more of a bell curvy looking thing than sharp peaks. But each of those kind of maxima are corresponding to a sort of perfect energy level that these molecules are able to absorb to excite their electrons to a higher energy level. Because those electron floor plans are going to be different for different molecules, you can therefore, by doing a sort of scan to see what wavelengths it absorbs and how much, you're able to tell kind of what molecule you have. And then if you know a value called an extinction coefficient, you can go ahead and calculate the concentration based on how much it absorbs, given the fact that the more of the thing that you have, the more of the light that you're going to steal, and therefore the higher the absorbance you'll see. There's a direct correlation between the amount of light that's stolen and the amount of molecules, and how given based on how much each molecule absorbs light. Therefore, you're able to determine how many molecules you actually had. Sometimes, if a molecule steals light, we can tell with our eyes. This is the case with visible things, with like dyes. If they're stealing visible light, then we're actually going to be able to see a different color. If you think about that white light that's coming out of your light bulb, it's got all the combinations of wavelengths of light. It's got all the visible light colors. And so if you have a molecule that actually steals one of those visible light colors, you're going to see something different. And so this is where you get like a color wheel. And if you steal one color, you absorb one color, you see the other colors. So if a molecule absorbs blue light, you'll see kind of orangish red light. And if it absorbs yellow light, you'll see purple light, etc., etc. The same thing is happening for light that we can't see. So we can't see ultraviolet light. It's too energetic. We can't see it. And so if it gets stolen, we can't tell with our eyes, but we can tell with a machine. So we can use a UV-Vis spectrophotometer. What it's going to do is it's going to shine light through the sample, and then it's going to see how much of that light gets absorbed. We can do a couple things. One is we can do a wavelength scan where we have it scan kind of all the wavelengths, or at least we tell it a variety of wavelengths. And so this is going to be limited by your machine, but you can do something where you're going to scan over a range of values, typically in this like UV visible spectrum. And so see here, we're typically looking at values around 220 to 350. We do some sort of scan. And depending on what molecule we have, we'll see different sorts of spectra. If you have DNA, what you're going to see is you're going to have a maxima around 260. And if you have protein, you're going to see maxima at 280 and 230. So what are these actually corresponding to? They're corresponding to the resonance stabilized regions of protein and DNA. So in your DNA or your RNA, this is going to be those nucleobases, so your ATCGUs, those actual base parts, they've got these resonance stabilized rings where you have these electrons being shared throughout the ring. In the case of our proteins, well, here we have our aromatic amino acids, so our tryptophan, phenylalanine, and tyrosine, as well as, I kind of just use the term resonance without really explaining it, but basically, if you think about covalent bonds, so actual bonds, not just interactions between molecules, those happen because atoms are sharing pairs of electrons. And if they have extra electrons, they can kind of do this thing called resonance, where they share the electrons between more than two atoms. So in the case of your peptide backbone, you're sharing it between the oxygen, the carbon, and the nitrogen, all in this kind of like commune. This has the effect of lowering the amount of energy you need to get between levels. So it's kind of like lowering the ceiling, making the floor shorter. This makes it so that you need less energy in order to get to the next level. And this is going to make it so that the light that you need to absorb is actually going to be in that range that we can measure. Note that if you think about, okay, so higher energy is going to be a shorter wavelength. Therefore, longer wavelengths, so things to the right over here, are going to have lower energy. And we can see that the rings, they're going to have a lot better resonance. They're going to have this really great resonance. If we think about a pure protein ring, like these tryptophan, phenylalanine, tyrosine, they're going to be absorbing this 280 nanometer light. Whereas the peptide backbone, well, here we don't have as much resonance. And so the energy that we need is going to be higher energy, shorter wavelength. It's a technical note. And if we were to think about like a dye, a colored dye, it would have to absorb an even longer wavelength of light, which would mean you would need even more resonance. And so dyes are typically going to have extended conjugation, so conjugation resonance, so they're similar terms that we use. So they'll have these ring structures where you see lots of kind of this resonance. And so often the resonance, you can kind of tell if something has resonance. If you look and see that there's kind of like these alternating single and double bonds, sometimes you might see things represented with like a dotted line. And in the case of our proteins, the main aromatic amino acids, so when we talk about aromatic, that's another word for when you have resonance in a ring, they're going to be tryptophan, phenylalanine, and tyrosine, with the major contribution coming from tryptophan. So all proteins are basically going to have a very similar absorption profile, with these peaks at 280 and 230. If you can take the absorption of one of those peaks and then use a value in extinction coefficient in order to say, okay, well, we know that this much of a protein should absorb this much light, and we absorb this much light, so we must have this much protein. then you can figure out how much protein you have. You might be thinking, okay, well, why don't we do it at 230? Isn't that where you get the most absorption? Well, if we look over here, nucleic acid is actually going to be absorbing quite a bit of 230, but not as much as 280. And so we kind of get a more specific measurement if we measure at 280. Additionally, that 230, you can also get absorbance from like salts and phenol, which are some things that you might be using in your extraction protocols. And so the 280 is going to be kind of more specific for your proteins. The 280 absorbance, this is not just going to depend on how much protein you have, but also the composition of the protein. Different proteins are going to have different amounts of tryptophan, phenylalanine, and tyrosine. Therefore, if you had the same amount of one protein that had a lot of tryptophan, it would be absorbing more light than that amount of a different protein that didn't have very much tryptophan. So we need to take into account a protein-specific value that tells us about how much light of our specific protein would be absorbed. This works great if you have a purified protein. If you don't have a purified protein, then you kind of need to use some generic value, or it might even be better to use a dye-based method that kind of just measures proteins more generically. But we're going to assume that we have a purified protein mixture. So Beer's law, or the Beer-Lambert law, tells us that the amount of light that is absorbed is going to depend on three different things. It's going to depend on the concentration of your molecule, so how many molecules there are in a given volume, the extinction coefficient, how well each of those molecules absorbs that wavelength of light, and the path length, so how much distance is that light traveling through. We can rearrange this to solve for the concentration, given the absorbance, if we know the extinction coefficient and the path length. The concentration in our Beer's law equation is going to be in molarity, so it's going to be in moles per liter. The path length, thankfully, spectrophotometers all kind of have a standardized path length typically of 1 centimeter, and the path length is going to be in centimeters in this equation. And so we can kind of just ignore the path length unless it's something different. And a note too that on a nanodrop, it typically has a conversion factor for you, so you don't have to worry about that. But 1 centimeter is the standard, so 10 millimeters, 1 centimeter, same thing. That'll cancel out. And so now, if you had take the absorbance and divide it by the extinction coefficient, you would get the concentration in molarity, moles per liter, which is great for some things. But often in the lab, what you're going to want is mgs per mil, which is the same as grams per liter. In order to actually get the mgs per mil or gram per liter from that concentration and molarity, you're going to need to know the molar mass, the molecular weight, and that will then allow you to do the conversion. Since your software knows that molecular weight and it knows the extinction coefficient, it can then take those into account to give you a conversion factor per percent weight volume. More in percent weight volume elsewhere, but by definition, a 1% weight volume is 1 gram per 100 mils, which is the same as saying 10 gram per liter. Often what you're given is going to be a 0.1% conversion factor. This 0.1%, therefore, would be equal to 1 gram per liter, which is the same as 1 mg per mil. Because there are 1,000 mgs in a gram and 1,000 mils in a liter, you can just multiply those together. And so what you get is that a 0.1% weight volume is going to equal a concentration of 1 mg per mil. The value you're getting is the absorbance that you would read if your solution was 1 mg per mil. So if it gave you a conversion factor of 1, that is saying that if you measured an absorption of 1, your solution would be 1 mg per mil. If you had a conversion factor of 0.607, that would mean that if you measured 0.607 as your A280, you would have a solution of 1 mg per mil. And if you measured an A280 of 1, that would mean that you actually had more than 1 mg per mil of your protein. And so maybe your protein doesn't have as many tryptophans, and so the same amount of your protein isn't absorbing as much light as the same amount of that protein that had the higher absorbance conversion factor, the higher extinction coefficient. So higher extinction coefficient, higher absorbance conversion factor, meaning that you don't need as much of the protein to get the same amount of light absorbed. If you know the extinction coefficient of your protein, and I'll show you how you can find this out, and you have a pure protein solution, well, then you can actually go and you can get the conversion factor for your specific protein. However, if you don't, or if you have a mixed solution of proteins, you can use a sort of generic version that's taken for a mixed protein solution to have an absorbance 0.1%. So remember that's 1 gram per liter or 1 mg per mil of 1. So if you were to go and measure an A280 of 1, that would say that you had 1 mg per mil of protein in the generic case. But your protein probably doesn't have exactly a conversion factor of 1. And so I'll show you how we can actually find the conversion factor. Note too that when you put it in a nanodrop, typically the nanodrop is going to want the 1% conversion factor, which means that you need to multiply the 0.1% factor by 10 before entering it. So you would enter 10 instead of 1 on the nanodrop. But the nanodrop, the kind of default, is going to be that 10 or that 1, however you want to think about it. But now say you have a protein with a different extinction coefficient, a different molecular weight, and therefore you're going to have a different conversion factor. I'll show you how we can actually go and find this for any protein, even like kind of custom proteins. But here's an example with bovine serum albumin, BSA, which is a common kind of generic protein we use in the lab. You can use this tool called XPazi-Prop-Param, and I'll show you how you can access it. It's going to give you two sets of extinction coefficients and absorbances. So remember the extinction coefficients? Those are going to be the actual things that you could plug into the Beer-Lambert law. And that would allow you then to figure out the concentration and molarity. Typically, however, we're going to be more lazy and we're going to use this pre-calculated absorbance conversion factor. Here you can see it's saying absorbance of 0.1%. So remember that would be 1 mg per mil. So here they're showing it gram per liter, but that's the same as mg per mil. And they're saying that would be 0.638, assuming all pairs of cis residues form cysteines. Then they're going to give you a second set of values, and this is going to be assuming all cis residues are reduced. Outside the scope of this post, but cysteine residues, so the amino acid cysteine, it can form crosslinks, it can form these covalent bonds with one another. And those are actually going to absorb more light than just the plain cysteine. And so what's going to happen is that you're going to get a higher extinction coefficient, a higher absorbance if you have oxidating conditions under which those cis residues are forming those crosslinks, as opposed to reducing conditions. In the lab, we're typically using reducing conditions, so we've added something like DTT maybe, beta-mercaptoethanol, and so we're going to be using this value that's assuming that all the cis residues are reduced. Although, in some situations, you might want to be using the oxidizing one. But in the lab, we're often going to be using this reduced one. And so we would say, okay, well, we have the absorbance of 0.1%, so 1 gram per liter, 1 mg per mil is going to be 0.607. This would mean that if we were to go and read an A280 of 0.607, we would have a concentration of 1 mg per mil. We take that 0.607, we divide it by 0.607, and we get 1. If we have less than that, say we had 0.203 as our absorbance, well, then we do 0.203 divided by 0.607 would be 0.334 mg per mil. If we had higher, we had 0.824, say, well, now we'd have 1.36 mg per mil. So we're able to directly go between the absorbance at 280 nanometer light and the concentration of our protein because we have a pure protein mixture and we know how much of the light would be absorbed for a given amount of that specific protein. So in this case, we had an absorbance 0.1% of 0.607. Now let's imagine that we had an absorbance 0.1% of 0.498, so lower. This would mean that for the same amount of protein, we would absorb less light. So if we were to measure 0.607 now, we would actually have 1.22 mg per mil because you would have to have more protein copies in order to get the same amount of light absorbed. So all these values are going to be higher, but we could calculate it in the exact same way Just now we're using a different absorption conversion value. Sometimes you might put that value directly into your machine, such as a nanodrop. So a nanodrop is like a normal spectrophotometer. So in the sense that you're shining light through and measuring how much gets stolen. But in this case, you're doing it on this tiny little pedestal in this tiny little minuscule column. And this is going to allow you to save your protein sample. So you don't have to use very much of your protein sample. You just put a little drop on it, you close the thing, and then it makes a little column that shines light and records. If you want to be more accurate, you can use an actual spectrophotometer where you're using cuvettes. You might need to dilute your sample first, and you don't want to waste your sample, so you either want to have a really clean vial, or you might want to use like a semi-micro cuvette where there's like a smaller little window, you waste less of your protein sample. That's going to be more accurate than the nanodrop. If you are using an nanodrop, you probably want to do a couple different tests of it. You can kind of take the average. They might vary a little. Make sure that you're blanking it with whatever buffer you're using. If you have like imidazole, that's going to greatly skew your values because imidazole is going to be basically the side chain of histidine. And so it's going to absorb a lot of light. And so you need to make sure you take that into account. So here's an example of how you could actually go and find the extinction coefficient and find those conversion factors. One place you can go is UniProt. This is basically the first place you want to go if you want to find out more about a protein, any protein. In this case, we're looking at the protein malic dehydrogenase from the bacterium Bacillus subfensis. There's a lot of things on this page, and there's going to be a lot more if you have a protein that's better annotated, so more is known about it. But if you go to the sequence function, you'll see the sequence of the protein. Sometimes you might see multiple sequences if there are different isoforms, but the first one's going to be the main one. If you go to Tools, you can go directly to Prop Param from right here. Now, this is going to give you a couple of options, and so they might show you if you just want to look at a different domain. But if you just kind of want the default, you can just press Submit. This is going to give you a variety of information. You can see it gives you the composition of the different amino acids. And then if you come down, it's going to give you extinction coefficients. Typically, it's going to give you multiple extinction coefficients. However, this protein, if we go and we look, it doesn't have any cysteine residues. Remember, the reason we got multiple before was because it would give us one where the cysteine residues form cross-links, so oxidizing conditions, and one where they were all reduced. If you don't have any cysteines, well, then you're not going to be able to form any crosslinks, and so you're just going to have a single value. But remember, if you have multiple values, you typically want to use the one with reducing conditions. For a couple of reasons, the main one being that in the lab, you're probably going to have reducing agents in your solution. And the reason why you typically include those reducing agents is because typically proteins are going to be in a reducing environment. Anyway, let's see what else this protein has. And so we can see if we want to think about which ones are actually going to absorb the most UV light, you're going to, our main one's tryptophan, and whoa, we don't have any tryptophan here. We do have some tyrosine, and we do have some phenylalanine, but no tryptophan. So we'd expect that our extinction coefficient and our absorbance conversion factors would be lower. And in fact, we can see that our absorbance 0.1%, so remember that's 1 gram per liter, would be 0.532. As opposed to kind of generic, which would be about 1. So if we were to go and we were to do our calculations, we're going to need to divide by 0.532. And if we were to go and stick it in our nanodrop, remember the nanodrop wants the absorption of 1%, and so we need to multiply this by 10 and stick in 5.32 rather than sticking in 10. This, however, is for the unmodified version. When I'm working with this in the lab, well, now I use a version in which I've added a his tag to the end. So these cysteines in a row, which are going to let me purify it. And there's also little linkers at the end before the start of the protein. And so I have extra amino acids. Because I can't just go to a default entry for this, I need to enter the sequence itself. You can do this by going directly to xBaseProp param. Now I can have it compute the parameters for this, and I get new information. I haven't added any tryptophan, so the value is still going to be low. If I look down here, well, now the extinction coefficient is actually lower than before because I haven't I've added more of those things that don't absorb as much, less of those things that absorb more. So my factor is now going to be different. And this would be the value that I would use. So I would divide by 0.498, or I would put in my nanodrop 4.98 as the 1%. If I was to cut off the tag and then not have the tag, well, then I have to go and look and see where the cleavage point is. But I can do this exact same thing. And so going directly to XBasy, putting in the sequence for your specific thing is going to be really helpful in the lab. But if you're working with like unmodified, untagged anything, then you can go directly from UniProt. So remember, just go to the sequence, go to the tools, and go directly to prot param from there. In addition to calculating protein concentrations, the A280 is also going to allow us to track proteins. And so if you're, say, doing a protein purification using column chromatography, you can use one of these FPLC machines, so fast protein liquid chromatography, in order to purify your proteins by sending them through these columns filled with these little beads called resin with different properties. Lots more other places, but basically the proteins are going to interact differently with the resins, and then they're going to travel at different speeds through the column, and therefore they're going to come out the other end at different times. And well, how do you know where your protein is? Typically, they're going to have a UV detector on the way to what we call a fraction collector, where they basically take little portions. Then you can compare those little portions where, like, you say, okay, well, I saw in this UV trace that I saw this big peak here at 280, which that's telling me that there's protein coming off there. And so now let me go and see which of those little tubes it ended up with and use those tubes. So UV-280 can be really great. You can track the progress of your run. You can see where the proteins are, so you don't have to go test each of those fractions individually. That's going to be tricked by the imidazole too, though, so be careful. A method that's less tricked by imidazole is a Bradford assay, and that's going to be a dye-based assay. It's also going to have some biases. There's also like a BCA, a Lowry, lots of different methods to measure protein concentration, and each of them kind of has pros and cons. More on that elsewhere, but this UV-280 is a really simple way that you can go about this. And it's also very useful for nucleic acids. But there, remember, we're looking at the nucleobase absorbance, whereas for proteins, we're looking at those aromatic amino acid absorbance, as well as looking at the absorbance from that peptide backbone. What do those all have in common? They've got the resonance. The resonance is decreasing the amount of energy needed to go between those electron levels, making it so that you can absorb light with lower energy, longer wavelength, light that we can actually detect with these machines. The protein is going to have a different spectrum than the nucleic acid. Nucleic acids are going to absorb primarily at 260, whereas proteins have peaks at 230 and 280. The 281 is more protein specific. In addition to having proteins and RNA also absorb significantly at 230, you can have salts, phenol, things like this, various contaminants. And so the 280 is going to kind of be more specific for your protein. And you can actually go and look at ratios of the different absorbance values to tell you about kind of the purity of your nucleic acid solution or of your protein solution. So if you were to take like a 260-280 ratio, what you would want for a protein would be around 0.6, but what you would want for DNA would be about 1.8 and RNA about 2. So that can kind of give you a sense of your purity.